Hello again, and welcome to our video for day 111. This is unit 1, day 11. Excuse me. We are going to split this into two parts, and we're going to see how we can use proofs and use some of these relationships with segments to write some proofs. And this is going to be a little bit different than the previous lesson. And when we get to part 2, we're going to be talking about angles. But in this first part, we want to go over some information about segment proofs. And I've given you this reference sheet. Now we're going to fill in some of this information. But the first thing I want you to pay attention to is this quick little review of our properties of equality. And you remember that was given to you on day 1.9 when we looked at doing some algebraic proofs. But remember, the properties above, or what we called our POEs, property of equality, they can only be used when we're dealing with an equal sign. Well, and everything we've done so far is just use an equal sign. But we can also talk about some other properties, in this case, properties of congruence, and we're going to call those POC, properties of congruence. And you'll notice some of the same key names, reflexive, symmetric, and transitive, but we can use those concepts to work with some proofs when we don't actually have an equal sign with actual values to substitute in for, but when we have just congruence relationships. And so the first part looks kind of like this. The reflexive property simply states for any segment AB, should have a segment line above it, the segment AB is always going to be congruent to itself. This does not make a lot of sense to why we would have to write that way, but as we go through some of our other proofs, you'll realize we actually use the reflexive POC quite a bit, property of congruence. We also have the symmetric property of congruence, and that states if we have one congruent segment relationship, so if segment AB is congruent to segment CD, I'm just making these up, pulling these out of thin air, then if I reverse that order, it's also true. CD has to be congruent to AB. And then finally we have what's called the transitive property of congruence, which is kind of like substitution, but there is no substitution when we're talking about congruence. When I'm using that symbol, I can't use substitution. I'm going to use what's called the transitive property. And there's going to be two pieces to this first part. If we have one segment congruent to another segment, CD, and then that segment, CD, is congruent to a third segment, EF, what I could just say is that the first segment, AB, is congruent to the third segment, EF. Okay, and we can use this kind of in place of substitution when we're using congruence instead of an equal sign. All right, and that leads us to some other ideas that we want to be able to use for basis of our proofs. And we've got a couple definitions here. Now, the definition of congruence is something that we actually need to use quite a bit. And what that allows us to do is to go from an equals relationship with numbers and algebraic expressions to a congruence relationship using symbols, kind of like this. Or it also allows us to go in reverse order, okay? If I start with this and I need to go to where I can use an equation and solve for something, that's what I have to use, the definition of congruence. And we just abbreviate that as def period of, and then our congruent symbol, okay? And that states this: if, I'm just going to use segments as my example, if I've got a segment AB congruent to segment CD, well then the length AB without the symbol is equal to the other length CD without that symbol. This is just a change of symbols. That's all this is doing, using the definition to change from equals to congruent or congruent to equals. So like we said a second ago, we can write this in reverse order. If I start with numbers, just the actual length AB equals CD, then they must be congruent segments with symbols. Okay? And then we also did our definition of midpoint yesterday. If M is the midpoint of AB, then AB equals C. I'm sorry, I've got to fix that. That's not correct. Give me just a second. What this should say is if M is the midpoint of AB, then AM equals MB. Part equals part. And we did that in the last lesson also. And while we're talking about the last lesson, we have what's called our segment addition postulate. Now, this must use equals, not congruent. So if I have to set up a situation like this, I'm going to use an equal sign. Again, this is still part plus part equals whole. BC must equal AC. Part segment plus the other part of the segment equals the whole segment. Okay? All right, and if you turn the page, you'll see we have day 111, part 2, where we're talking about angle proofs. Instead of splitting this into 2 separate days, we do have just a quick little review of our properties of equality again. Properties of equality, again, is what I was trying to say. POE. But then we also have from the previous page those properties of congruence, POC. But then we also have some definitions for angles that are important, and you don't have to write anything down. So we are going to kind of go over this quickly together. I'm just going to read these to you, and I'll try and make sense of it. So make sure your volume is turned on so you can hear what I'm saying. The definition of congruence, again, applies to angles also. So if I have equal angle measures, I have congruent angles, and vice versa. This double-ended arrow just means I can go in both directions to change an equal angle measures into a congruent statement, or a congruent angles back into an equals so I can solve an equation. Definition of angle bisector we talked about in day 10. Okay, it divides it into 2 equal parts. Definition of complementary and supplementary are very important. They allow us to set up equations also. So if I know that 2 angles are complementary, I can set up an equation that their measures equal 90. Or supplementary, I can say their measures add up to 180. And then definition of perpendicular and definition of angle of a right angle are also going to be used in this lesson. So if we were to try and use the definition of complementary angles here, we would be setting up an equation where a measure of an angle plus the measure of another angle equals 90, or measure of an angle plus measure of an angle equals 180, depending on which one of these 2 words we're using. And then we also have our angle addition postulate. This is another form of part plus part equals whole again. But then there are some other theorems we are going to need to use in this lesson. And those are here. And so we're going to take a look at those, and there's nothing to write down. So I'm actually going to kind of cover these more in class as we talk about them, but they are going to be kind of important to us. And there's one of them we're going to actually change, so I'm going to make sure we talk about that in class. But right now we're going to take a chance to look at some examples. So what I want you to do is turn your page back to the, I'll show you, to the back of this page, okay? So we've got our day 111 part 1, and we are going to do an example or 2 of actually doing a proof on the back of this page. So what I want you to do is, in a moment you'll see my example written down, and I want you to pause the video and copy that down, and then when you're ready to actually go through the lesson with me on that example, you can push play again. Okay, this is what we're going to do for our first example. This is a segment proof, and if you haven't copied this down yet, again, pause the video, make sure you have it copied down. Here's what we're given. We're given some segment where E is the midpoint of DF, and I'm not giving any algebraic information. There's no expressions using X to plug in. We just want to use the segment relationship postulates, theorems, definitions, properties, all those things to prove that 2 times DE equals DF. These are not 2 different variables. This is the length of DE. In fact, I could put parentheses around it if it makes it easier to understand. 2 times the length of DE has to equal the total length of DF. And so this is what we're going to do. We're going to start with our first statement. I don't even have to make the columns if I don't want to. I can just make a list. So I'm going to write the first statement as my given. E is the midpoint, and you can abbreviate, of DF. And then in parentheses, I'm going to write my reason that is given. This is another way to organize a 2-column proof. You can just make a list of your statements, and then each reason is given in parentheses. Okay, and in order to set this up, what I want to do next is use the given information to come up with another statement. Well, the midpoint word, by definition, tells me that part equals part. So I'm going to use that definition to say DE equals EF, because I want an equation here using DE and DF. And so the reason for that is definition of midpoint, or midpoint def. Okay? Now from there, I'm using another basic concept of any segment, and that's just part plus part equals whole. But I'm going to get more specific with the midpoint. And so you might have to use that, and it seems kind of out of the blue, but anytime I'm using a segment like this and I'm equating the whole thing, df, to something else, I probably want to start with part plus part equals whole. But I'm going to fill in these expressions. de is the first part, plus ef is the second part, and that has to equal the whole thing, df. Now, if you'll look at this, I'm using de and ef again, and since they are equal to each other, I could use substitution in a minute. But for right now, I'm just going to explain where I got this equation, and that is from my segment addition postulate, or part plus part equals whole. So I'm going to call that seg add post, segment addition postulate. Now I'm going to use some information here. All right. Since I have this equation, and DE equals EF, but I'm trying to show that DE times 2 equals DF, I'm going to do a little bit of substitution. I'm going to say that DE plus DE again equals DF. Because all I'm doing is substituting, instead of this expression, I'm replacing it with another DE. So that's substitution. Okay? And then I'm going to simplify this side, because any value plus itself is the same as doing 2 times that value. So 2 times DE has to be equal to DF, which is what I was trying to prove. And if you write it with parentheses, that's fine, or you can use the dot, or you don't have to. You can make it match exactly the way I wrote it originally. But all we did was simplify this side by combining those like terms. So you can write combine like terms or simplify. Okay? And that finishes our proof. That's what we were trying to prove. And so that's a way we can use segment relationships in a proof. Okay, we're going to go ahead and do one more example to finish our video out, and we're going to do an example about angles. So if you have room to write it down below on this page, go ahead. Otherwise, turn to the back of your Day 111 Part 2 page, where we have some space there, and we will do our next example there. This is what I want you to use for your next example, so you're going to want to pause the video once you see it and copy it down, and then we will be ready to work that example out. Okay, this is what I want you to have. Again, you'll want to pause the video if you need to. We are dealing with angle bisectors here, and we're going to use a diagram like this where I actually have some overlapping angles. And so I'm going to show you how we're going to do this. We're told that BE, that ray, bisects angle ABD. So that means these two angles are congruent. We're also told that BD bisects angle EBC. So these two angles would be congruent. Well, if you look at our markings, that means all three are congruent to each other. So of course, ABE, this first angle, and DBC are going to be congruent, but we're going to walk through a proof that shows why that is using some properties and definitions that we've been talking about. So first, I want you to write this. Our givens, I'll put them all together. Okay, kind of like this. If I'm moving too fast, I'll just pause the video so you can get caught up. And then we want to move from that information to eventually saying these are congruent angles. Well, that really means I need to explain what bisect means. And so what we're going to do is we're going to say, and I'm going to actually combine some steps here to make this as short as possible. If this is an angle bisector, we're going to say that these angles are congruent. Angle ABE is congruent to angle EBD. Sorry, don't forget your angle symbol. But then also, because of this statement, I know these angles are congruent. Angle EBD is also congruent to angle DBC. And that's just by definition of what the word bisect means. And so our reason is bisect definition. Well, look at this. We've already said one angle is congruent to a second angle. That second angle here is also congruent to a third angle. That's enough to say that these first and third angles are congruent. Angle ABE is congruent to angle DBC, which is what I was trying to prove. The reason is the transitive property of congruence, or trans POC, which you'll remember is kind of like substitution for congruence. Okay, we don't actually call it substitution because there is no substitution property of congruence. I have to use what's called the transitive property here. And that's what I was trying to prove, and that finishes that proof. Okay, and so we're going to do more examples and we'll get more practice with this in class, but this at least is a starting point for you to be able to work with some proofs where I don't actually have equations to use. So make sure these notes are complete and you bring them with you to class, and we will move from there.